interestingly, this chapter has content that we've seen at least somewhat in other chapters. And so a lot of what we'll see here will have a familiar ring to it because of that. Ethers, their structural nature is such that I've got an oxygen bridge between two carbon-containing groups. R and R prime here are alkyl or aryl groups. What does an aryl mean? Aromatic rings. Okay, so alkyl means just ordinary hydrocarbons. Aryl means aromatic. Okay, so here is a dimethyl ether. That's a dialkyl ether. And here's an aryl alkyl ether here. The one on the left is symmetrical. The one on the right is not. It's unsymmetrical. By symmetrical, we mean what? Same thing on both sides of the ether. The ether linkage is interesting in contrast to some things we've already seen. For example, here's the dimethyl ether we were just looking at. The oxygen is a tetrahedral oxygen. It's sp3 hydrolyzed. The oxygen has two non-bonding pairs of electrons, and the bond angles between the carbon groups ought to be tetrahedral, 109.5, and you can see that they are in fact close to 75. They're a little further apart than that because these methyl groups sterically interfere with one another, and that tends to open the bond up just a little bit. All right? The bonds are polar. They're a dipole. There's a net dipole, as we see here, going that direction. So this end of the molecule will be somewhat positive, this end negative. And this moderate polarity will play into some of the ether's properties, along with the non-bonding pairs of electrons. Now, boiling points for ethers are comparable to those of hydrocarbons of the same molar mass. So we look at dimethyl ether here, which has a molar mass of 46, and propane, which has a mass of 44, and the ether's a little higher, but not much, about 17 degrees. Notice that substances that have OH groups like water, ethyl alcohol, and butanol have much, much higher boiling points. And why is that again? For the hydrogen bond. Notice that the ethers have pretty good dipole moments, but there's not a corresponding jump, well, not a big corresponding jump in boiling point as a consequence. And ethers can take on a variety of forms. Here I've got a simple symmetrical dialkyl ether. This is a cyclic ether, tetrahydrofuran. Here is the one that we normally refer to as ether. This diethyl ether is the one that's used normally as, in fact, it's so commonly we just call it ether, or ethyl ether. The ether bond can act as a hydrogen bond acceptor, but not a hydrogen bond donor. What does that mean?
I mean, they can't, it's not like, you need both to have hydrogen bonding. So it doesn't bond with itself, probably hydrogen bonding oil.
If I have an ether,
It's kind of like male and female.
notice that there's no hydrogen on the oxygen here to form hydrogen bonds with other ether molecules. But if I bring a water molecule or an alcohol, hydrogen bonds can form. And so we call the ether a hydrogen bond acceptor because it accepts the hydrogen from a protic substance that it does hydrogen bond. Does that make sense? What this means is that the ether cannot hydrogen bond with itself. Hence the lower than expected boiling point. You know it's quite polar. You don't see a big jump in its boiling point because the ether is no hydrogen bond with itself. But what would you predict about the solubility of things like alcohol and water in ether?
High.
Yeah, either high or at least moderate, because they can form those kinds of interactions with those alcohol or those OH, those hydroxyl groups. Okay, okay? And so, no hydrogen bond with the ether, but we do see with an alcohol or with water, the good potential for the hydrogen bond to take place. And ethers generally will have good solubility in alcohols and vice versa. And they will have, interestingly, we refer to ether as, and in the laboratory, you'll do ether and water mixtures and they'll form two layers. What you can't see is that about 10% of the ether has gone into the water and vice versa. And so even though there's a distinct layer separating the two, there is a fair amount of solubility and miscibility taking place because of this effect. Now, it turns out that ethers have some unique properties in terms of solvating ions. For example, lithium iodide has a pretty good solubility in ether. Okay, here's my lithium ion, which is small. It's a positively charged ion, and so the non-bonding pairs of electrons on an ether molecule will complex with it. And that will solubilize the lithium ion. And so I could take lithium iodide and it will dissolve in ether, whereas it might not dissolve in pretty much any other organic solvent because of this effect. Lithium fluoride. Same thing. Fluoride itself, hydrogen bonds with alcohols and ethers. But in this particular case, the ether is good for dissolving some salts. And we've seen evidence of this in some reactions we've already encountered. For example, the Grignard reagent. Remember that ether, diethyl ether, is strongly needed or strongly required. Here's the Grignard reagent. Here's this would be, we'll say this is bromide, this is methyl magnesium bromide. The non-bonding pairs of electrons on the ether oxygen complex with the magnesium ion and stabilize it. So the ether has the ability to stabilize not only the formation of the Grignard reagent, but it increases solubility so that we can use it in a reaction. So this sticks around for a while. We use tetrahydrofuran, that's this ether, this cyclic ether, in reactions where we use boron. And sometimes you'll see it shown this way. Notice that the non-bonding pair of electrons in alcohol are donated in a coordinate covalent bond to boron. Why would that happen?
Because it doesn't have.
Yeah, boron only has, if I look at boron, and this stuff is not very soluble by itself. Notice boron doesn't have an octet. And so putting in a solvent like ether, where a non-bonding pair of electrons can be donated, then I can stabilize it by giving it its octet. Boron, or borane, likes to be in this form because of that reason, when it's by itself. But when I put it in ether, I stabilize the BH3 form. I'm not going to draw that for you, by the way. That's a real bizarre.
I was just going to say, where do the electrons come from? If it doesn't have them.
It looks like that.
Oh, okay.
And so I've actually, and you might think that all sorts of violations of bonding principles you learn in violated, and in fact they are. This is what's been proposed, but in this particular case, these borons are connected. Notice the borons have an octet. Who's being forced to behave? And the hydrogens are this guy has got. And just recognize that the diborane is the natural form for borane when it's by itself. And when I put it in ether, I stabilize the borane form, which is the kind that does the reactions we discussed previously. We've seen crown ethers before, and mostly just in passing. But crown ethers are great big ether structures, poly ether structures actually, and each of these corners is a CH2. And so what I have here is a series of ethers that can surround in circular fashion a cation, and form multiple complexing interactions with the cation, and they're sized appropriately for a particular cation. This one here, for example, is an 18 crown 6. What does that mean?
6 oxygens.
Yes, 6 interactions, 6 oxygen interactions. 18 is what?
The carbon, maybe?
Yeah, it's the number of the ring components. And that, in fact, that's how these things are actually made. So,
Wait, how come, wait, 1, 2.
how many atoms are in the ring surrounding the potassium? Counting the oxygens.
1, 2, 3 times 6, 18. Oh, because there's an oxygen, 2
Yeah,
carbons.
the oxygens are counted. So there's 18 atoms in this great big ring, 6 interactions. And so it's called an 18 crown 6. That size is used for potassium. Now, if I wanted to, where could I use these again?
Because then like,
Yeah, or even SN1, but SN2 most particularly. Suppose I had CH3, CH2Cl, and I wanted to react iodide with it. I know that iodide is a great nucleophile, right? And so iodide can attack here, and the chloride comes off, and I get substitution, SN2 substitution. Question is, how in the heck do I get that to dissolve in a non-polar organic solvent? The answer's over there on the board. If I take sodium or potassium iodide plus the crown ether, the crown ether solubilizes that guy and turns the iodide loose. Does that make sense? And so this turns out to be a way to get powerful nucleophiles into solution that ordinarily would not be expected to go in. And in the solid form. Okay, so sodium, potassium, and lithium would be used here, provided I use the right crown ether tool.
well, you write crown, yeah, right, because we're not going to pick up a bottle of crown either, right?
The crown ether describes the general category, but this would probably be on a bottle, would be called an 18 crown 6. And
Like, okay. So you don't know if
I'm
it's a
missing
diet.
the point of your
Oh, no,
question.
John's making fun of me if this is going
That's
like
to be
what,
expected.
like how would you know if like a diethyl ether, or I don't know how, would you know what kind of an ether to put in water now? It doesn't matter.
No, you mean that, for example, if you wanted to use potassium bromide or something,
Okay.
you would go to the literature and say, all right, what crown ether do I need to get the potassium dissolved? And you look it up and it says 18 crown 6, and you go to Aldrich or Sigma, one of the chemical companies, and buy some.
So it's an ether that comes looking like that ether
Yeah,
up there?
it's already made.
It's already bonded to
You
the-
buy it.
Okay, all right.
And notice without the potassium in there, it's just a great big cyclic
All
ether.
right. Okay.
So the potassium's actually bonded to the oxygen.
Yeah, it's not, they're actually complexing bonds where the potassium, because it's got, and when you look at potassium particularly, it's in period 4. It's got some d orbitals where it can tuck electrons, and it has great capacity to form these complex interactions. All metals do, but once we get down farther on the table, they can form more bonds. Notice that the sodium does 5 and lithium only 4. So as the ion gets smaller, has less capacity to do this. If I did this with HI, it probably wouldn't dissolve in an organic solvent. It's just too polar to do it. And if I did KI, this would not dissolve in a solvent, it would dissolve this. So the crown ether allows me to put it in there and let it come into that contact. Naming ethers. Very, very commonly still called by an old style method.